on page 615, we're starting with reflections. Now, the learning target here says that we're going to draw reflections in a plane and in a coordinate plane. So in a plane means no x and y axis, just a plain piece of paper. In a coordinate plane, well, x and y axis. Using paper, we'll do that. Transparencies, even though that's part of the standard, we won't because there are no transparencies on standardized tests. Graph paper, we'll do that. And in a couple days, I'll finally remember to get you some graph paper. If you've got some, fine. For today, we can just sketch an x and y axis. Tracing paper, I don't even know what that is. Software, well, on a standardized test, you're not going to be using software. So we'll be doing these on our paper with graph paper and without graph paper. All right? And then all that came from the standard. Now, this second learning target I came up with simply because it doesn't make sense to me to be doing reflections if we don't know what one is. Okay? So the second learning target, define reflection. And let's actually begin there. On page 615, here's our definition. A reflection in a line maps a point. Okay, so we're reflecting points, okay, to its image such that, remember the notation or the vocabulary that the book uses. The pre-image is the original figure, the image is the new figure. All right, so maps a point to its image such that, you're going to love the first one. If the point is on the line, then the image and pre-image are the same point. So if you look at this figure right here, point A is on the line of reflection. K is the line of reflection. So when you reflect it, A prime, its corresponding point. See, isn't that nice? A and A prime, so you always know what matches up to what. B prime will correspond to B. X prime will correspond to X. Okay? So A prime is also in line, the exact same point. So if a point is on the line of reflection, its reflection is the same point. So don't you hope there's a bunch of those ones. Now here's the one that we're going to do a whole lot more of. If the point does not lie on the line, meaning line of reflection, the line of reflection is the perpendicular bisector of the segment joining the 2 points. Here's an example of that. A is not on the line of reflection. A prime, and I'll show you how to figure out where A prime goes. Okay? A prime is on the other side of the line of reflection. If I draw a segment connecting A and A prime, the line of reflection is perpendicular to that segment connecting A and A prime, and it bisects the segment connecting A and A prime. Now, let me show you how this is done. Okay? I copied this example 1 out off of page 615. Let me just talk about it briefly, then we will do a couple of reflections together. All right? So, first, look up here where the check mark is. Triangle ABC, the line of reflection is K. Here's what we're going to do. We're going to take our straight edge, and we're going to make a dotted line from each vertex of our figure that we're going to reflect. And then we're going to have to be real careful where the dotted line goes. The dotted line has to be perpendicular to the line of reflection. So we'll lay our straight edge down, and we'll make a dotted line from A past the line of reflection, perpendicular to the line of reflection. Then we'll go move our straight edge over here to B, make it so that it's perpendicular to the line of reflection, make a dotted line. Then we'll do the same thing from C. Then we take our compass and we measure the distance from A to the line of reflection. And then we put A prime, that exact same distance, on the other side of that line of reflection, using that dotted line to line them up. Then I measure the distance from B to the line of reflection. Using that dotted line, I put B prime the exact same distance away. Measure the distance from C to the line of reflection. Use that dotted line to put C prime the exact same distance away. Then I connect the vertices, and I have the reflection. Let's do it. Number one, from page 619. So, copy the figure and the given line of reflection. So, using your straight edge, just like with constructions, nothing is free-handed. How much is free-handed? Nothing. Use your straight edge to make a triangle that looks about like that one does. Make sure you put point D on the line of reflection. Go ahead and make your line of reflection horizontal like this one is. So your triangle is not going to look exactly like this one, but make it look kind of sort of like it. And we are going to draw the reflected image using A as our line of reflection. Now it says using a ruler, straight edge, where most of us have a protractor as our straight edge. Okay. Everybody got triangle CDF and the line of reflection? Here's what we do next. And this is really the hardest part. Is because we're going to have to eyeball it and do our best to make a line that's perpendicular, a dotted line that's perpendicular to that line of reflection. So put your straight edge down so that you can start at C and make a dotted line that's perpendicular to the line of reflection. And make it nice and long on the other side of the line of reflection. Because again, like the constructions we did earlier, we're going to leave all this other stuff on there. We're not going to erase the part that's not the reflection. We'll leave it all. That way I can see your marks and see that you've done it correctly. Okay? Nice and long. All right, now point D is on the line, so we know that D prime will be on the line. F, make sure it's perpendicular. Now, here's one way you can tell a little bit. Okay? Since both of those dotted lines are perpendicular to the line of reflection, doesn't that mean they're parallel to each other? So your dotted lines need to look parallel. It's not going to be perfect, but they need to look parallel. And they need to be as close as you can get them to being perpendicular to the line of reflection. It's not going to be perfect. All right? Everybody going to be able to live with that? It's not going to be perfect, but we can get as close as we can get. And with practice, you can get really close. Okay? So we've got our dotted line. Now take your compass, and we're going to use it as a measuring instrument. Put the point of the compass on point C and adjust it so that the pencil is where the line of reflection is. So the point is on point C, the pencil is where the dotted line crosses the line of reflection. Now, using that setting, look up here at the screen so you see what I'm talking about. Using that setting, move the point of the compass to the intersection of the dotted line and the line of reflection, and then make a little arc across the dotted line. Everybody see what I've done? Then we move to point D, but remember, D is on the line of reflection, so D prime is the same point. So let's move on over to F. Put the point of your compass right on point F. Adjust your compass setting so that the pencil is on your line of reflection. Then pick up your compass, keep that setting, pick up your compass, put it on the intersection of the dotted line and the line of reflection, and make an arc across the dotted line. So does everybody's drawing look about like mine does? Now, where we went from C and then measured off, that point is C prime, isn't it? where we measured from the dotted line from F, that point is F prime. And then D prime is the same as D. So label that as D prime as well as D. So now we've got C prime, D prime, F prime. Use your straight edge to connect the vertices. So you connect C prime and D prime, C prime and F prime, and D prime and F prime. So triangle C prime, D prime, F prime is the reflection of triangle CDF. They're congruent to each other. Now remember that strange part of the definition that said the line of reflection was the perpendicular bisector of the segment connecting a point and its image? Well, look, and you're done. The reflection is done. So don't write this on your reflection. But you need to know this segment right here and this segment right here are congruent to each other, aren't they? Because F and F prime are the same distance away from the line of reflection. They must be. This segment here and this one here are congruent to each other because C and C prime must be the same distance away from the line of reflection. That's why D and D prime are the same point, because D is not any distance away from the line of reflection, so D prime can't be any distance away from the line of reflection. So we made this fit the definition. All right, you guys with me? You see how with a little practice you can get really good at these? All right, let's do another. Number 2. So on your paper, go ahead and make a quadrilateral that looks more or less like QRST. And this time, make your line of reflection slanted a little bit like this one is. That's not quite vertical. And this will make it tougher. Dealing with things that are horizontal and vertical are simpler than dealing with things that aren't. In theory, it shouldn't make any difference, but it seems to. So everybody, use your straight edge to make QRST. Use your straight edge to make the line of reflection. Everything you do, you use your straight edge. And now, for the toughest part, we try to make the dotted line that's perpendicular to our line of reflection. So I'm going to start with R, because I think if I have a little distance, maybe it's a little easier to tell. And line up your straight edge and get as close to perpendicular as you can get. So y'all help me out. Look at the screen. Does that look pretty perpendicular? Does it? Yeah, I think so. All right, now, like I told you before, since they're all your dotted lines are supposed to be perpendicular to the line of reflection, they should be parallel to each other. So, when we make these lines, when we're finished making our dotted lines, they should all be parallel to each other. Now, yours is going to look a little different than mine because your QRST is a little different than mine. Anybody get there so that when they made the dotted line, 2 of the points were on the same dotted line? Somebody did earlier today. That's okay. I mean, if you tried to do it on purpose, you'd probably never do it, but yeah, that can happen. Okay? So, are we all full of dotted lines? All right, now, get your compass. Move your compass point. I'm going to start with R. Start with whatever point you want. I'm going to put the point of the compass on R. I'm going to stretch the compass out so that the pencil is on the line of reflection. Then I measure that exact same distance R prime is the same distance from the line of reflection as R is. Then go to a new point. Point to Q. Use your compass to measure the distance from Q to the line of reflection. And then put Q prime the same distance away on the other side. And then do the same thing for all your remaining points. Use your compass to measure the distance from the point to the line of reflection. Then put the corresponding point the exact same distance away on the other side of the line of reflection. Label your new points using that prime notation. So you'll have Q prime, R prime. Oops, I labeled mine wrong already. That wasn't Q prime. Here's Q prime, R prime, S prime, T prime. Then use your straight edge to connect them. You got a question? My guess is, without looking, if yours turned out really weird, your dotted lines may not be perpendicular to your line of reflection. Is that what it was? I'll come look at it in just a second. That's usually what happens if it looks really weird, is your dotted lines aren't perpendicular to your line of reflection. Okay, so with some practice, we can get pretty good at doing these. But it is going to take a little practice. Make sure your make sure your dotted lines are perpendicular to your line of reflection, and we should be okay. Now, let's take a look at number 4. All right, I'm still on page 619, number 4. Taru is waiting at a cafe for a friend to bring him a ticket to a sold-out sporting event. At what point P along the street should the friend try to stop his car to minimize the distance Taru will have to walk from the cafe to the car and then to the arena entrance? All right, well, I'm not sure I'd be that concerned about my friend. I'm bringing him a ticket. He can walk a little bit. But let's pretend that we are. Let's pretend that we're nicer than I am. And we want to make that distance as short as we can. Have you ever heard this before? The shortest distance between 2 points is a straight line? It's true, isn't it? So what we want to do is we want to turn this into a linear kind of problem. And I've got it written in blue up here. Here's how we do that. Since he's at the cafe, I made the entrance to the cafe point C. If I reflect point C in line S, S for street, so the edge of the street is a line, and then I want to put point P on that line S, the line of reflection, so that E, P, and C prime are collinear. Okay, that's a bunch of foolishness, right? On your paper, don't draw the picture of the building, but put point C, point E, and that line of reflection just like I have it on here. All right, so look, I could move that, and it would still work out okay. So you need point C, point E, and the line of reflection. So as everybody's drawing look about like this, we're going to reflect point C in line S. All right, so we need a dotted line. Oops. Nope, just C. All right, so we've got the dotted line from C perpendicular to line S. Well, you know what to do next, don't you? Oops, I'm still making lines over here. Take your compass, put the point at C, adjust your compass setting to measure the distance from C to line S. Move your compass to the other side of the line of reflection, and C prime is the same distance away from line S as C is. And I think this next part's kind of neat, because now I'm going to connect E and C prime with a dotted line. And guess where P goes? Where the dotted line connecting E and C prime intersects the line of reflection, that's where point P goes. So that's where you need to park your car. Get it? P for park. Clever, aren't it? So look, remember, shortest distance between 2 points is a straight line. We took the reflection of C, called it C prime, and so then found the shortest distance between E and C prime. That's where, we need to park along that shortest distance. Well, assuming you're not going to run into the lawn of the sports arena, the only way you can park along that line connecting E and C prime is right there on the street. So that's why P goes where it goes. And now you see where to park. Cool, huh? All right. Now, if it were me, yeah, you'd be walking. I'd be like, you want the tickets? You know where I live. And bring your money. All right. So we've done all of these reflections so far without using a coordinate plane. Now let's use a coordinate plane. Number 5. So if you don't have graph paper, and most of you don't, that's fine. Just draw an XY axis on your paper. So it's going to be inexact because you're making your own XY axis instead of having it on a piece of paper for you, but that's okay. We can still make it look really good. And then go ahead and graph triangle ABC. A has coordinates 1, 1. B has coordinates 2, -2. And C has coordinates 7, 2. So you'll know where to put A, B, and C. So graph those points, connect them, and you'll have triangle ABC. All right, now, here's the nice thing about a coordinate plane. It's already got perpendicular lines, and it's easy to measure because all you have to do is count spacing. Okay? So we're going to be doing the same thing we just got through doing with our compass and protractor, but now it's actually easier to measure. It's easier to get perpendicular, right? Because horizontal lines and vertical lines, perpendicular. And it's easier to measure because we just have to count spaces. So for number 5, y equals -2 is our line of reflection. So graph the line y equals -2. Use your straight edge. And now remember how it works? So in effect, the vertical lines from the grid are now our little dotted lines, aren't they? So A is 3 spaces above the line of reflection. So doesn't that mean A prime has to be 3 spaces below the line of reflection? So 1, 2, 3, that's where A prime goes. B is on the line of reflection, so B prime is the exact same point. Yeah, the original A is 3 spaces above the line, so A prime goes 3 spaces below the line. C is 1, 2, 3, 4 spaces above the line, so C prime goes 1, 2, 3, 4 spaces below the line. Then use your straight edge to connect the vertices. And you reflected triangle ABC using y equals -2 as your line of reflection. Now everything works the way it did before. The segment connecting A and A prime is perpendicular to the line of reflection, isn't it? Same thing with C and C prime. B and B prime are the same point because they're on the line of reflection. So instead of using a compass to measure, we use spaces on the coordinate plane to measure. That's the only difference. Make sense? All right, let's take a look at number 6. So graph the same triangle. A still has coordinates 1, -1. B is still 2, -2. And C is still 7, -2. So graph that same triangle again. And this time we have a different line of reflection. And while you're doing that, I'll say this again. I think I've said it once, maybe I haven't. The image we come up with is always congruent to the pre-image, isn't it? The new figure is congruent to the old figure. It's got to be. Seven, 2. Now, our standards call this kind of transformation where the new figure is congruent to the old one a rigid motion. So if you see the term rigid motion, that's what we're doing here. All right, x equals 3. All right, if y equals -2 is horizontal, what's x equals 3? Vertical. So use your straight edge to graph the line x equals 3. And then let's reflect each point. A is 2 spaces away from the line of reflection. So where's A prime go? 2 spaces on the other side of the line of reflection. So there's A prime. B is 1 space away from the line of reflection. So B prime is 1 space on the other side. Now, A was on the left, B was on the left, A prime on the right, B prime on the right. Well, look at C. C is already on the right, so where's C prime going to end up? On the left. So it's what? 4 spaces to the right? So C prime has to be 1, 2, 3, 4 spaces to the left, and then we connect. Then we connect our vertices. A prime, B prime, C prime is the reflection of ABC. Notice in this case, the line of reflection is right. Middle might not be the right word, but it's in the middle, right? Part of the figure, part of the original figures on the right, part of the original figures on the left. Part of the reflected figures on the right, part of the reflected figures on the left. Any questions? Okay. Now, so on a coordinate plane, we can count spaces. Also, on a coordinate plane, if our line of reflection is one of three special lines, we don't even have to count spaces. We can figure out what the new coordinates are going to be just by learning this little trick. That's the right word, I don't know what else to talk. So, look here. If we're going to do a reflection in the x-axis, it says to reflect a point in the x-axis, multiply its y-coordinates by -1. Now, why on earth would that work? Well, look here. Here's point A. See where I just made point A bigger? Its coordinates are 4, 1. If I'm going to reflect it in the x-axis, so that red line there is the x-axis. If A is one space above the line of reflection, shouldn't A prime be one below? And isn't 1 below the x-axis a y-coordinate of -1? And then B was 3 spaces above, so B prime 3 spaces below. I like this notation here. We'll use this some more later on. XY becomes X negative Y. I actually say XY is mapped onto X negative Y. I like become the area. The point XY becomes the point X negative Y. So, go ahead on your paper and draw an X and Y axis, one of each. And then graph triangle XYZ. X, Now, could I simply count spaces, just like we did on 5 and 6? Yes. Okay? I could. But, if you can remember this, to reflect a point in the y-axis, multiply its x-coordinate by -1. So, look, I'm going to make it blue on mine. The y-axis is our line of reflection. Again, I could count spaces, but to use our new little hint here, x prime's coordinates are going to be, leave the y-coordinate alone. Oh, I shifted it now. I showed you x-axis, and now I'm working on y-axis. Okay. To reflect a point on the y-axis, multiply its x-coordinate by -1. Sorry, I didn't mean to mix them that. Does that make sense to you, though? It's the same idea, just going left, right instead of up, down. Okay? So, since our line of reflection is the y-axis, we multiply the x-coordinate by -1. Well, 0 times -1 is still 0. The y-coordinate stays the same. You get y prime. -3 times -1 is +3. The y-coordinate stays the same. to get z prime. Negative 4 times negative 1 is positive 4. The y-coordinate stays the same. Well, so now, x and x prime are the same point, aren't they? Y prime has coordinates 3, 4. And z prime has coordinates 4, negative 1. Then we use our straight edge to connect. Like so. Sorry I showed you x-axis and the theorem and then did y-axis. But it amounts to this. Okay? Here's the key. If our y-axis is our reflection, we're flipping everything right to left. So the y-coordinates don't move, the x-coordinates do. So we multiply by negative 1. Alright? We ready for number 8? On number 8. Now, let's do number 8 before number 7, but now we're going to reflect in the x-axis. Since the x-axis is horizontal, reflected in the x-axis reflects up and down. So it's the y-coordinates that are going to change. The x-coordinates are staying the same. The y-coordinates will change. So, let's graph this. Q is negative 1, 4. R is 4, 4. S is 3, 1. And T is negative 2, 1. So, could we do this by counting spaces? Yes, we could. Okay? But, there's our line of reflection. Our rule says multiply the y-coordinate by negative 1. So for Q prime, leave the x-coordinate alone, multiply 4 times negative 1 and get negative 4. For R prime, leave the x-coordinate alone, multiply the y-coordinate by negative 1 and get a negative 4. For S prime, leave the x-coordinate alone, multiply 1 by negative 1 and get negative 1. For T prime, leave the x-coordinate alone, multiply 1 by negative 1 and get negative 1. So, Q prime, there, R prime is there, there's S prime, there's T prime. Now, something I didn't point out on 7, probably should have, I'm going to point it out now. This is still the same thing we were doing with our compass and protractor. Look, if I connect T and T prime, the segment that connects them, is it perpendicular to the line of reflection? Yep. Is T the same distance away from the line of reflection as T prime? Yeah. If I connect R and R prime, is the segment connecting those perpendicular to the line of reflection? Yes. Is R prime the same distance below the line as R is above the line? Yes. So we're simply using our coordinate plane, and if you remember it, your little rule here, to help you speed up the reflection. Okay? All right, so far so good. There's one other line that we need to get really good at reflecting with, and that's the line y equals x. Here's the rule for line when you have your line of reflection is the line y equals x. We interchange x and y coordinates. That means just switch this. Don't change signs, nothing. So if a was negative 2, 3, a prime would be 3, negative 2. Okay? You simply switch the x coordinate with the y coordinate. That's what interchange is. Okay? If y equals x is your line of reflection, it always happens. Let's do one of these. Now this time I'm not going to draw the line of reflection in yet. Okay? So we have quadrilateral JKLM. I got to hurry. The bell's going to get us. So let's graph this. J is negative 3, 1. K is negative 1, 3. L is 1, 3. And M is negative 3, negative 1. Negative 3, negative 1 for M. Now, according to our rule, since our line of reflection is the line y equals x, we interchange the x and y coordinate. So J prime, J is negative 3, 1, so J prime is 1, negative 3. K is negative 1, 3, so K prime is 3, negative 1. 1, 3 becomes 3, 1. Negative 3, negative 1 becomes negative 1, negative 3. And then let's graph these. So J prime is 1, negative 3. K prime is 3, negative 1. L prime is 3, 1. And M prime is negative 1, negative 3. Now, behold, I'm going to draw in the line of reflection now. Isn't that neat? See how it all works out? If I connected L and L prime, would that segment be perpendicular to the line of reflection? Sure. If I connected any pair of corresponding points, that segment will be perpendicular to the line of reflection, and L and L prime the same distance away on opposite sides of the line of reflection. Same thing with K and K prime, and so forth. Now, at the bottom of page 618, they summarize that. The only one, reflection in the x-axis, we can do by counting spaces. Reflection in the y-axis, we can do by counting spaces. This one, we really do need to remember the rule, don't we? Because wasn't that, what we did there, a lot easier than graphing the line y equals x and then using your compass and protractor to do the reflection? All right? So you really do need to remember that rule right there when that's your line of reflection. Keep in mind, our goal is for you guys to ace the ACT. Are you going to have a compass and protractor with you on the ACT? So what kind of reflections will they ask you about on a standardized test? The ones on a coordinate plane. Okay? Now, sometimes they'll ask a procedural question. They'll ask you, like, the steps for doing it without a coordinate plane, or maybe you have to put the steps in the correct order, but it's much more common for them to ask you about things in a coordinate plane, because it's just easier to ask the question, isn't it? From the test maker's point of view, it's a lot easier to ask a question about that. They can just ask you what the coordinates would be and know whether or not you can do the reflection. Okay? Now, here's the assignment. Here's the assignment. So on page 619, 1 through 12, 16, 17, 30, 31, 36, 41, 46, 52, and 55.